Good morning. We started doing studying 1D maps last time, and just to recap, we were doing the logistic map, and the logistic map was given by the following equation. Of course, we had the discrete time, and this is how, or this was the recipe for the subsequent iterates of the map. And just reminding you, x was in the range 0 to 1, and we chose r to be in this range, and this ensured us that the map gets mapped back to 0 to 1. Map is mapped back. And of course, we graphed it. The last time, and this was r by 4, and the maxima occurred at half. This was okay. So and we saw the iterates of the map. Let's say picking a value of r 2.8, we saw that as time progresses, starting from some condition, it reached a fixed point x star, and the x star did not depend upon the initial condition. Similarly, for r equals to 3.3, we had some sort of a, of course all this is, but the bottom line is that it reached a period 2 cycle, and this is much like as we discussed the limit cycle for continuous time dynamical systems, and subsequently we had a period 4 cycle, so on and so forth. And the bottom line was that well, let's just draw the period 4 cycle, which occurs as we crank up r eventually. So this was n, and it went somewhere from bup, bup, and finally you had some behavior which was some sort of a periodic behavior. So this was a period 4 cycle after some initial transients. And we saw that as one cranks up R, one goes from period 1 to period 2, period 4, which is nothing but 2 to the power of 2. This is 2 to the power of 1, so on and so forth. And at certain discrete values of R, period doubling occurs. So that was the story. And one of the questions we wanted to ask was, of course, where does the period doubling occur? Also, one might ask, what is responsible for this period doubling? I mean, what is responsible? Of course, one answer is that cranking up R is responsible, but what exactly is happening in the parlance of the dynamical systems? What's really happening? What's the underlying reason? What happens as we crank up R? So these are the questions which we would like to ideally answer in this particular lecture. And we also talked about some notions of universality, which either we are going to look at it in this lecture, time permitting, or we might have to go to the next lecture for looking for it. So let me just write it as a case for universality. And we said that qualitatively speaking, any map with a hump shape will have such a behavior. So for showing this sort of a universality, we need to at least develop a geometric understanding of the problem. And of course, we saw that Rn, let's denote that by the value of R, where the 2 to the power of nth cycle occurs. And remember, we saw R1, R2. So R1 was 3, where the period 2 cycle occurs. R2 was 3.449, where the period 4 cycle occurs. This is 2 power 2. So on and so forth till R infinity. So we are going to look that in some detail as well. Starting from the equation, now we saw that x star equals to 0 is always a fixed point for any r. By the way, before that, we can actually draw some diagram as a function of r. This is the fixed point 0, and at r equals to 1, I have another fixed point, and then a period doubling occurs, then something again, period doubling occurs, so on and so forth. So this is r equals to 3, so on and so forth. This was r equals to 3.449. So this is always going to be a fixed point for any r. So what happens near this fixed point? So I'm going to neglect the quadratic terms because near the value 0, the quadratic terms are second order in a very second power of a very small number. So I'm just going to neglect it. So I can write my map as roughly x1 is r times x0, x2 is nothing but r times x1, or in other words, r square times x0. Remember, x1 indeed was actually r x0 times 1 minus x0, and I'm just neglecting the quadratic term out here. So going like this, I get x to the power of n is r to the power of n times x0, and you can look, this is depending upon r greater than 1, keeps growing exponentially, and r less than 1 decays to 0. So therefore r less than 1, this fixed point is stable. So remember the stability of the fixed point x star depended upon the slope or the derivative, whether it's less than or greater than 1. At least that was our linear stability analysis. And what do I have? I have, for the map, I have, well, if I have fx as this guy, then that is just r minus 2r x, and at 0, this guy is nothing but r. That's what we saw above, that r less than 1 implies linearly stable. So I had that in my picture. I had an R, and starting over here, this guy was, of course, X till R equals to 1. 0 is stable. The moment R becomes greater than 1, the fixed point remains, certainly. This is going to be a fixed point for any value of R, but it loses stability and pops up another fixed point, which we are going to see. So this is the other fixed point. The other fixed point. And as I crank up R, this fixed point is going to change location, and then I'll have a period doubling thing, and so on and so forth. Okay, so why don't we look at it? The other fixed point. The other fixed point I get by solving this equation. Now, of course, I'm going to neglect the x star equals to 0 fixed point, so that just gives me the other fixed point as this guy. And the slope, so I'm using the symbol x star for both the fixed points. It should be clear from the discussion and the context which fixed point I am referring to. So the slope it gives me is two minus r. And of course, we know that for stability, the slope should be less than 1, or r should be between 1 and 3. So for this range, the other fixed point is stable. We already saw that. This was R, this was the location of the fixed points. So for till R equals to 1, I had the 0 is stable, and the other fixed point was, so the first fixed point was this, the second fixed point was 1 over 1 minus R. So for the moment R becomes 1 or greater than 1, pops up the second fixed point in the range 0 to 1, that's why. And this guy is stable till R equals to 3. That would be the location of a period doubling, which you are going to see now, but that's the idea. The other fixed point is stable. Okay, very good. So we can also look at it graphically, what's happening, and Now let us sketch out the map itself. Uh, it's always nice to draw this diagonal line, which is this line. And let's analyze some case where R is some number less than 1. I start here as my initial condition, and well, the next iterate is going to be over here, x1, which is the definition of my map. Now, on this graph, how do I find out x2, which is going to be this guy? So this is x1. For that, I need to locate where on the x-axis this guy x1 is. So for that, I just take it over here, and this was the location of x1. I go down here, this is going to be my x2, and for further iterates, I'm going to feed this x2 back in the map. So this was x2, and now x3 is going to be rx2, 1 minus x2. For that, I need to locate where x2 is on the map, and for that, I again try to hit this line. This is gives me x2. So you can see this zoom, zoom, zoom. It's sort of in this graph. It's further iterates. They are now converging to x equals to 0. So these are, you can regard them as staircases or cobwebs. But that's in some sense a nice way to see how, starting from any condition, the cobweb leads me to a stable fixed point over here. So we can try another example of the staircase. It doesn't really matter. Let's say pick up another guy. This is xn, this is xn plus 1, this is y equals to x. Okay, so again we see we'll converge back to some fixed point over here. So this was another example with r less than 1. Let's see what happens when r is greater than 1. Let me draw this guy. This is xn equals to xn plus 1. R greater than 1 would be a curve which is going to be slightly having a steeper hump. So this is r greater than 1 case. And I start with some x0. Let's say I can start it anywhere, doesn't matter. I see this is x1, and I'm going to find where exactly is x1. On the x-axis, this is where my x1 was. That led me to over here on the next iterate, that gave me x2, and so on, x2, x3, so on and so forth. So yeah, let me draw slightly This is r greater than 1, but I made it too steeper. This is r less than 3 also. We'll come to the case where r greater than 3 is also there. So we can see that the staircase, which, or the cobweb, which diagrammatically represents my future iterates, that converges to the other fixed point. So this shows that I asymptotically reach the other fixed point. So not only I have one more fixed point in this case, it is stable. So we have both seen it algebraically as well as geometrically, uh, what's happening. So by the way, let's see the case when R is 3. So what happens when R is 3? So I again draw this guy. And I draw this line, which is my, and this is my curve. And as we know, my slope of the other fixed point was 2 minus r. So at r equals to 3, this gives me minus 1. So this slope is, I can use a different color. The slope is minus 1. And what happens over here? So I'm going to just blow this guy up. So blow this guy up. So I have, just zooming in on this part, blowing this up, I have, very close to this fixed point, actually the tangent itself is the curve. So I have two lines. This was my diagonal line, xn equals to xn plus 1, and this was my curve. And as I can see, they are intersecting each other at right angles. And what do I get? I get, from my cobweb diagram, I sort of cycle around. So I would start at some sort of a point. I'm going to zero around here. In order to find the next iterate, I go here, because that's going to be my, so let me call this P, this point is Q. And I'm going to just cycle around over here. So these are the 2 points on the curve. I can call them P and Q. And by the way, this is all zoomed up diagram at r equals to 2. These points P and Q would be very close to each other, but that's the idea. Because I am intersecting at right angles, and this is very near the zoomed out snapshot of this curve. So this P and Q are going to cycle. And that essentially means that now I have got a period 2 cycle. So this is going to circulate around 2 points on the curve, and geometrically speaking, I have the condition for period doubling. Uh, well, the condition is that you intersect the diagonal line with a slope of -1. That's exactly what happening. We showed geometrically. So when R is 3, we have for the other fixed point -1, and this gives rise to this condition gives rise to period doubling. So remember the errors we talked about, the error of the iterate versus the error of the previous iterate, that was -1, and that was the condition for period doubling, as we have shown. So this was the error in the n+1th iterate, and this was the error in the nth iterate. And we can look at it up in our bifurcation diagram. I had R, this was X, there was the stability, 0 was stable, then I had one more fixed point, and I had at R equals to 3, this was R equals to 1. And as I crank up R, I'm going to get these two fixed points which we saw diagrammatically. And these are the period 2 points. Of course, I can also algebraically calculate them. So what happens at these period 2 points? Of course, we saw that it keeps hopping around this guy, from this guy to this guy. So in other words, I get f of p over here. F of p equals to q, and f of q equals to p. Or in other words, a function applied to p twice gives me p back. So these are the period 2 points. And of course, I can solve for this guy algebraically. I'll just plug in again f of p. So you can immediately see that things become messier, but this is actually a 4th degree polynomial. And which is in general, I mean, we can solve it, but it becomes more and more complicated. So before explicitly solving it, let's look at it, what really is happening. So notice that the period 2 points are the fixed points of this particular map. which is the map applied twice. So let us look at that. How would the map applied twice look like? So this is the map for f square, and I have the iterates, my usual iterates. So this is this guy, and I have my diagonal line. Now, of course, depending upon the shape or the value of r, it's a degree 4 polynomial, so in general this is going to have some more bumps. Of course, I'm not drawing it, I'm just sketching it very roughly, and this may intersect at 4 points, may intersect the diagonal at 4 points, 1, 2, 3, 4, or at some other value of the parameters, it can just intersect at only 2 points. So this was p equals to f square p, and the question arises that by the way, if you look at this map, this was x equals to 0, x star equals to 0, or x equals to 0, which was the fixed point of this was not a period 2 point, this was a fixed point which is always going to be, no matter what my map is. As we saw, x star equals to 0 is always a fixed point. We have another such point which was the fixed point of the map, not the fixed point of f square, but it was the fixed point of the original map fxn, and that, if you look at it from graphically, if you look at it, this was this particular point, and I had the period 2 points p and q hovering around it, zoom, 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 zoom. So this point, the other fixed point, was always sandwiched between p and q. So this was my other fixed point, x star. That was the other period 1 point, or the fixed point. And these guys were my p and q. And how do we solve for p and q? Well, we notice that p equals to f square p. This is the equation we have to solve, because ultimately p was f of q, q was f of p, implied p was the fixed point of this map f square. We know that for this equation, x star equals to 0, and x star, the other fixed point, which was, I don't remember, it was I think 1 minus 1 over r. Let's just look at it. Yeah, this guy. These guys can be factored out from my fourth degree equation. Fourth degree equation, and I can find p and q explicitly. After that, it's a quadratic equation, and of course, once I have p and q explicitly, I can also find the condition when do these guys get unstable. I just note down the page numbers. And the answer to that question is it happens when R2, as we have discussed, is 1 root 6, which was something like 3.449 dot 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 dot. And remember 3.449, that was when the period 4 cycle occurs. Over here. And the story continues. When the period 4 cycle gets unstable, I have the period 8 cycle. So on and so forth. So once again, I mean, you can see geometrically as well that we have a qualitative geometric understanding of what's going on. Uh, and not only the algebraic equations, but how we have through the staircase or the cobweb diagram, how we get a period 2 cycle, period 4 cycle, so on and so forth. So this geometric understanding is going to help us or aid us developing some arguments about universality of such a behavior that perhaps we'll study in the next lecture.